Hello everyone, welcome to SEDA Lighthouse Project Season 2. Today we're gonna talk about the graph convolution networks. Myself here, Rupesh Bharadwaj KR. The graph neural network is one of the trending topics among AI researchers and scientists, which has the unique ability to solve real-world problems by using graph data. In this series, I'm going to explain you how graph neural network works, the history, the applications of graph neural network. Let's discuss a bit about what is a graph data. Graph data is a way of organizing and representing data in form of nodes and edges. Nodes are also called as vertices. The nodes represent individual objects or entities, and the edges represent the connections or relationship between them. Let's think of a social network like Facebook, where each user is a node and each connection between the users, such as a friendship, is an edge. In graph, these nodes and edges can be represented as points and lines. In recent years, the use of graph data has increased in areas such as machine learning and data science, where the graph-based model and algorithms are used to analyze and make predictions based on complex relationships such as the spread of a disease through a social network, the flow of traffic through a transportation network, or the interaction between the protein molecules in a biological network. These graph algorithms and models can be used to extract insights and make predictions based on the complex relationship between entities. Let's consider an example of a movie graph data, where nodes are the individual people and the edges are the relationship between them, such as an actor or a director. In transportation navigation graph data, where the nodes are the travel destinations and edges are the estimated travel time, speed limit, traffic, and mode of transport. In chemical reaction graph data between atoms, where individual atoms are nodes and the different types of bonds are the edges. Then graph neural networks have their roots in field of artificial neural networks back in 1940s. However, the specific idea of using neural networks to model complex graph structured data emerged more recently after 73 years. In 2009, the paper titled The Graph Neural Network Model was an influential paper that introduced a novel neural network architecture based on a recursive message passing scheme, where each node in the graph aggregates a message from its neighboring nodes and then applies a nonlinear transformation to the aggregated message to compute its own hidden representation. The resulting hidden representation of all nodes in the graph are then passed through a readout function to produce the final output. Moreover, this paper can be viewed as a precursor to modern graph neural networks. Post 2010, there had been a paradigm shift in graph neural networks, which had brought us several innovative papers contributing to the development of GNN. Let's look upon graph neural network classified papers. In 2016, Graph Autoencoders was published. In 2017, Graph Convolution Neural Networks were published. In 2018, contributed to three major papers such as Graph Attention Networks, Graph Recurrent Neural Networks, and Graph Convolutional LSTM Networks. And in 2019, Graph Transformer Network was published. Let's discuss a brief about types of graph neural network and its use cases. Graph autoencoders. Graph autoencoders are used for unsupervised learning on graph structure data. They try to learn a compressed representation of the graph that can be used to reconstruct the original graph. Graph autoencoders are used for tasks such as like anomaly detection and network visualization. Graph convolutional networks. Graph convolution networks uses a graph convolution operation to aggregate information from a node's neighbor and generate a new representation for that node. This operation can be applied to multiple layers of a neural network to learn increased complex representation. Graph convolution networks can be used for applications such as like node predictions, network classification, graph generations. Graph attention networks. Graph attention networks uses an attention mechanism to weight the contributions of each node's neighbor when computing the new representation for that node. This allows the network to focus on most relevant information of each node rather than treating all neighbors equally. Graph attention network also used for tasks such as node classification, link prediction, graph generation, semi-supervised learning, knowledge graph, and community detection. Graph recurrent neural networks. In graph recurrent neural networks, the graph is traversed in a sequence of node visits, and at each visit, the representation of each node is updated based on its own previous representation and those of its neighbors. Graph recurrent neural networks have been applied to a variety of tasks involving graph structure data, including node classification, link prediction, and graph generation. Graph convolutional LSTM networks. The graph convolutional LSTM networks combines graph convolution operation with the recurrent neural network operation to process graph structure data. However, there is a difference in specific type of RNN used in each approach. Graph recurrent neural network uses a standard RNN architecture, whereas a graph convolution LSTM network uses a long short-term memory architecture, which is a variant of RNN. LSTMs are designed to address vanishing gradient descent problem that occur in standard RNNs. By using a memory cell and a gating mechanism to control the flow of information through the network, this makes graph convolution LSTM network better suited for modeling long-term dependencies in the graph data. Both graph recurrent neural networks and graph convolution LSTM networks have been shown the effective of graph-based tasks such as node classification, link prediction, and graph generation. Moreover, the choice between the two approaches may depend on the specific characteristics of the dataset and task which we need to handle. Graph Transformer Network. The Graph Transformer Network are a type of graph neural network that uses a transformer architecture to process graph structure data. Transformers were originally developed for natural language processing tasks and have since been applied to a wide range of other domains, including computer vision and speech recognition. The graph convolution neural networks are a type of neural networks that can operate on graph structure data. GCNs are inspired by the success of convolution neural networks, CNNs, in image processing tasks and they extend CNN to work with non-Euclidean data structures like graph. In graph convolution neural networks, the key idea is to define convolutional filters that operate on the graph structure. These filters can be applied to the nodes in the graph, taking into account their neighbors and their respective edge weights. The output of the convolution filter is transformed version of the node's feature vector. Let's understand how the aggregation of input graph is computed in a simpler way. The input graph has 6 nodes in ranges from 1 to 6 and it has connected edges between them. Let's take target node 4 and look how the computation graph is being done. The target 4 defines a computation graph where each edges connected directly to the target 4 transforms to an aggregate function. Likewise, each node defines its own computation graph and each edges in the graph is an aggregate function of it. Let's get bit deep about aggregation and resulting feature vector of graph convolution networks. For each node in a graph, its feature vector is first transformed using a learned weighted matrix. Then the transformed feature vector of the node's neighbor are then aggregated by computing a weighted sum. Generally, the weights are determined by the edge of the graph and can be computed using a softmax function to ensure that they sum up to 1. Later, the aggregated feature vector is then passed to a nonlinear activation function such as a rectified linear unit ReLU, and finally the resulting feature vector is the output of the graph convolution layer for that node. This process can be repeated for multiple layers of neural network to capture more complex features of the graph. Moreover, in each layer, the feature vector of nodes are being updated based on the feature vectors of the neighbors, which allows the network to capture local and global structure of the data. Aggregation is a crucial part of graph convolution networks as it enables the network to capture relationship between the nodes in the graph. One of the major advantages of graph convolution network is that they can operate on graphs of arbitrary size and structure, making them to solve real-world problems. The design of convolution filters and the choice of hyperparameters can be a challenging task in graph convolution networks. The choice of filter, the depth, and the number of features can have a significant impact on performance of the graph convolution network. The design of convolution filter is problem specific and requires more domain knowledge to define meaningful filter that can capture relevant features of the graph. Another challenge of graph convolution network is the computation complexity, which can be high for large graph. The computation of adjacent matrix and the multiplication with the weighted matrix can be expensive, especially for dense graphs. Several techniques have been proposed to address this issue, including graph spacification and parallelization. Despite these challenges, graph convolution network has shown promising results in a variety of applications, and they are an active area of research in machine learning community. In the traditional machine learning model lifecycle, which requires a domain expertise and extensive feature engineering to extract relevant features from the raw input data. In contrast, graph neural networks can automatically learn features of nodes and edges from raw graph data. This is especially useful in scenarios where the graph structure is more complex and difficult to model manually. GNN can learn features that are specific to particular graph structure, which can capture the interaction between nodes and edges in more accurate way. Moreover, GNN can handle various types of input data, including graphs with different structures, size, and characteristics. They can learn from the input data and capture the underlying patterns and relationship without requiring any prior knowledge about the graph data or the graph structure. This makes GNN more versatile and adaptable to different use case and applications. Overall, the ability of graph neural network to learn from graph data without requiring extensive feature engineering is a significant advantage that can save time, effort, and improve the accuracy and performance of the models. Hey everyone, let's get our hands dirty by implementing the node classification using graph convolutional networks with a simple example. In node classification, we use to classify nodes in a graph based on the features or property. In our case, we have two-dimensional space of nodes and edges. So nodes are represented here as 0, 1, 2, 3, and 4, 5. And edges are represented in form of two-dimensional space in 0, 1, 1, 2, and 2, 0, where 0, 1, 2 are the index of the edges in represented. So we are defining the size as well. So here the size we have given as 2, 4, 1, where 2 is the size of the input layer. So that's the number of features per node, where the 4 is the size of the hidden layers and 1 is the output layer. So 1 will be the output layer for each nodes which we have. So totally we will be getting a 3 outputs from it in a matrix format. So let's go into node classification function. So node classification function takes in three parameters: nodes, edges, and size, as we defined earlier. So now we're going to compute adjacent matrix for the graph, and we're going to set the values of matrix to 1 for each edge in edge tensors. Later on, we're going to compute the linear transformation layer for each layer using a linear function. At last, the sigmoid function is applied to the result of a linear transformation of adjacent matrix and the node features. The resulting node represents the values in between 0 and 1, that which represents the node's activation or importance in context of graph. In our case, we have a output of 0.53 on all three nodes, which has a equal importance, say is 50% equal importance on all nodes. Therefore, a higher output value would indicate the node has a stronger activation, or it has more importance to the nodes by itself. So let's uh, wrap up here and stay tuned for next update with a greater implementation of GCNs. Thank you.